Hello all, I'm Naren from Shastra Deemed University, Tanjavur. This is a short video on numerical problems related to fixed and fluidized bed system. This is part of the fluid mechanics course for the beta chemical engineers. I hope you have seen the part 1 video on this fixed and fluidized bed where I shared a few glimpses on the derivation of Ergun equation. So this is the part 2 of that video sequence where we'll talk about what kind of numerical problems are expected in this topic. So I hope you have seen the textbook and now you are well aware of the derivation of the Ergun equation and you know the Ergun equation. I have quickly written here what the Ergun equation, which helps us to compute the frictional pressure drop across a fixed bed or a packed bed system. Delta Pf by L, where delta Pf is the frictional pressure drop across the bed of length L, is equal to 150 mu u bar epsilon s square divided by phi square dp square epsilon cube plus 1.75 times of rho u bar square epsilon s divided by phi dp epsilon cube. Epsilon is the voidage or the fluid holdup or the gas holdup or the liquid holdup in case gas or liquid is flowing through the bed. Epsilon s is the solid holdup. So epsilon s and epsilon are related by the expression that epsilon plus epsilon s is equal to 1. So that's what is given here. Rho and mu are fluid properties. Remember, particle density is nowhere used. This is a fluid density and the fluid viscosity. dp is the mean particle size. Typically the Sauter mean is used, and phi is the sphericity of the particle. If sphericity is not there, we can typically assume it to be 1. L is the length or typically the height of the bed part alone across which this frictional pressure drop is computed or is to be estimated. This u bar is a superficial velocity. What I mean by superficial velocity is the volumetric flow rate divided by empty cross-sectional area of the bed. So that is given by Q by A. A is the empty cross-sectional area of the bed. So if you assume bed to be cylindrical, so A is equal to pi by 4 d square. Now at this point, just think of is there any orientation going to matter in terms of this computation? So this is something that I want you to think. Next, a small exercise that I want you to do before I proceed to the numerical problems is you take this Ergun equation, you rearrange this equation. What I mean by rearranging is you either add, multiply with the same terms or take some terms out common from these two, rearrange to right hand side or left hand side. You rearrange and bring the equation in this form. Okay, so you have to take this Ergun equation, rearrange the Ergun equation into this form. So in this form, this REP is a particle Reynolds number given by this expression where rho and mu are again fluid properties, u bar is a superficial velocity and dp is the particle size. So if you rearrange this Ergun equation in this format, can you identify what is this term which is denoted here as x? So I want you to find out what is x in this. So we'll take it up probably during our online interaction what this x is all about. Now this is not an exhaustive list, but broadly we can have 3 different types of problems in this topic. One is fairly straightforward, like where you given the flow condition you will estimate the pressure drop. The second one, the operating condition is known and you have to find the operating condition, but the pressure drop is known. And the third one is the particle size has to be found out and you already know the flow rate and the frictional pressure drop. Let's take each one of these categories or the cases of problems one by one. So in the first one, the fluid properties are known. What I mean by fluid properties is rho and mu is known. The operating condition is known. So the operating condition could be either volumetric flow rate or mass flow rate or the superficial velocity. The bed dimensions are known. The bed dimension is the diameter of the bed or the height or the length of the bed. And the particle properties are known. What I mean by particle properties here is the particle size and the sphericity. Typically hold up or the void fraction should be given as part of the question, but if it is not there, we can safely assume this. Can you think of what is the typical value of this solid hold up? You just go through the textbook or think on for a moment. If you take a solid bed, right, and fill it with solid particles, what could be this? Maybe I'll just take a small time here to show what I mean by here. Let's say that we take a bed. So let us assume that this is a bed. If we fill it with all solid particles, let us assume that I am filling it with all solid particles like this. So let's say everything is filled with solid particles. So these are all, let us assume that it is closely packed. So I have filled. So whatever is the unshaded region in this, so let me just mark, this is the unshaded region which I am now showing in uh, dots. This unshaded region is actually the void fraction. So what do you mean by the void fraction is, if the fluid has to flow, the fluid can only flow through this part. Now, if you have a packed bed system, can you estimate what could be this void fraction? So what could be this volume of that is occupied by the fluids to the total volume that is of this system? So if I take a small system, pack it completely with beads, is there any guess? Is there any nominal value for this void fractions? This is what I want you to think. Let's go back again to the document. So the first problem is a fairly simple. So you can just write down the Ergun equation, identify, you just see both left hand side and right hand side, identify which are all the knowns and unknowns, and then see how to solve this category of problem. Let us again do this. Let us write Ergun equation. So we have delta PF, frictional pressure drop per unit length, is 150 mu u bar by phi square dp square. Now it's an easier way to remember. So you just need to write first the viscous term. The viscous term is linearly in terms of velocity, and then in the denominator it is actually the square of the linear dimension, in this case the particle size, and this will be always have a cube of the void fraction or the fluid hold up, and the numerator you will have solid hold up, so epsilon s, and the power on the epsilon is always the power of the particle diameter. So the second term, so the coefficient is 1.75, because this is the inertial term or the kinetic energy term, so we can write as rho u bar square. Now already you have rho u bar square, so here the denominator is just phi into dp. Now this again will be multiplied in the denominator always by cube of the voidage fraction or the void fraction, and the numerator you will have solid hold up. The power on the solid hold up is same as the power of this. So this is how you can easily remember your Ergun equation. Now if you see this type 1 as shown here, so you are already given the fluid and properties. So the fluid properties is known. So you are given the particle dimension, so that means sphericity and particle diameter is known. The solid hold up or the voidage fraction is assumed, so that means this is also known. So you are given the operating conditions. So the moment you are given the operating conditions, we can write mass flow rate is the density of the fluid times volumetric flow rate, and the volumetric flow rate can be written as cross sectional area of the bed by superficial velocity. So that means these two terms are also known, and you also know the bed dimension, so that means the length is also known. So that means the only unknown in this case is the frictional pressure drop. So this is fairly straightforward. Everything on the right hand side is known. The only unknown is the frictional pressure drop. So that means if you just substitute, you will get to know the frictional pressure drop. Just make sure when you substitute all units are consistent. So that is why if you see here, I have given the typical units, SI units of all the terms. So you have to just make sure all the units are in consistency. So I hope this is okay. So and we can go for the second category of problem. Now in the second category of problem, the fluid properties are there, the bed system is there, particle dimensions and sphericity is given, pressure drop is known, solid holdup can be assumed, or the voidage fluctuation can be assumed. What is unknown is the operating condition. So again, go back to an Ergun equation. So whichever is known, I have put a stick mark here as red. So the unknown is basically the u bar, right? Now if you see this in one term, the u bar is linear, so you have u bar as power 1, and in the second term it is u bar squared. So that means it looks like a quadratic. So can you rearrange this term as a quadratic expression? Maybe you can pause the video and take a minute to rearrange this as a quadratic equation. Now if you have rearranged the equation in terms of ax squared plus bx plus c, it should look something like this. So I have collected all the terms which are together with the square of the velocity. So this 1.75 rho epsilon s divided by 5 dp epsilon cube as this term, and the next term is 150 mu epsilon s square divided by 5 square dp square epsilon cube. This is primarily this term. So this is probably the b term, and now this term is brought to this side, so your c is actually having a negative coefficient. So this is a quadratic equation in u, and the only unknown is u here, everything else is known. So you know the roots of the quadratic equation, then it can be readily solved. So let's go to the third type. Now in the third type, again the fluid properties are known. So the bed dimensions are known. The pressure drop is known. The operating conditions are given either as volumetric flow rate or u bar or as m dot, mass flow rate, average velocity, or the volumetric flow rate. What is not known is the particle size. Now solid holdup is either given in the question or it is assumed. So again look into the Ergun equation. Now whichever is known, I have just put tick marks. The unknown is the particle size. Now this again can be rearranged in terms of a quadratic expression. Again, I request you that you just pause for a minute, rearrange this equation, collect the coefficients of the square term and the term with respect to dp power 1. Try to see if this is a quadratic expression. So here again one will arrange, if you have done, so you will get such an equation. So we can collect all these terms which are with the square term, and this is all with to the power 1 on diameter in the denominator in this case, and this term should be brought to here. So you will have like this. So this will also look like a quadratic expression, but the only difference is x is equal to 1 by dp. Now that means this also you can be solved. So that means what we have seen in this lecture is there can be broadly three type of problems. One where operating condition is known, and that is fairly straightforward. You will find the pressure drop. The second one is the operating condition. What I mean by operating condition, the flow rate has to be computed and the pressure drop is known. And the third one is the particle size has to be found out if and this pressure drop and flow rate is known. So I request you to once again go through this video probably and reflect on the type of unknowns, and then take up the tutorial problems and then solve it. We'll definitely meet over the interaction instruction and clarify the doubts. Thank you all for your patience listening. See you. Bye.